Hello everybody. This is a very short video with a summary of Unit 6, which deals with organometallic compounds containing sigma donor ligands. As indicated in the course syllabus, this unit comprises alkyl metal derivatives, stability, alpha and beta hydrogen elimination, agostic bond, and agostic bond. We will also include in this unit aryl metal derivatives. This table lists different organic ligands that coordinate to transition metal through sigma bonds. While alkyl ligands have virtually no pi acceptor ability, some of the other sigma donor ligands have also empty orbitals with pi symmetry and can form also a pi bond by backbonding, giving rise to a stronger metal-carbon bond. Alkyls are typically very strong anionic sigma donors, second only to hydrides. From the viewpoint of the metal-carbon bond, the donor strength of alkyl ligands increases when hydrogens are replaced with hydrocarbon groups such as methyl, ethyl, isopropyl, but caution, steric factors can come into play and weaken the metal-alkyl bond. For example, terbutyl groups are often too sterically hindered to bind well. On the contrary, replacing the hydrogens with electron-withdrawing atoms such as fluorine, dramatically reduces the donor ability of the alkyl or aryl groups. Metal alkyls are also typically very reactive to oxygen, water, etc. Let's talk now about the stability of the alkyl metal derivatives. But before that, let's go back to our first day class. Remember that the successful synthesis of main group alkyls, remember that almost every non-transition element had been shown to form stable alkyls. Well, after that successful synthesis, many attempts were made to form transition metal alkyl, but most of them failed. Now we know that those failures were due to kinetic and not to thermodynamic reasons. Metal-carbon bonds are strong. By the way, remember that opposite to main group metal-carbon bonds, the energy of transition metal-carbon bonds increases with the increase in the atomic number. That is, going down a group. I was saying that transition metal-carbon bonds are strong, but the existence of several easy decomposition pathways makes many transition metal alkyls unstable. So, in order to be able to design stable alkyls, we must look at some of these pathways to see how they can be inhibited. The major decomposition pathway for alkyl complexes is beta elimination, which converts a metal alkyl into a hydrido metal alkene complex. We have already studied it in Unit 5, so let's just remember here that in order to have a beta hydride elimination, you must have beta hydrogens present on the alkyl ligand, and also must have an empty orbital on the metal in a cis position to the alkyl ligand. The electron count on the product alkene hydride is 2 electrons more than that of the alkyl starting material. An 18 electron alkyl is much more reluctant to beta eliminate via a 20 electron intermediate That is a 16-electron alkyl, which can go via an 18-electron alkene hydride. Beta elimination is not favored then in 18-electron alkyl complexes. Even if the alkene subsequently dissociates, which is often the case, we still have to stabilize the transition state leading to the alkene hydride intermediate if we want the reaction to be fast. An 18-electron alkyl, on the other hand, is said to be coordinatively saturated. By this, we mean that an empty orbital is not available. Some 18-electron alkyls do beta eliminate, but detailed mechanistic study often shows that a prior dissociation of some ligand is required. Remember that the main driving force for beta hydride elimination is the formation of a stronger metal-hydrogen bond, usually stronger than metal alkyl, and the generation of an alkene ligand that reduces the unsaturation of the metal complex. To have a kinetically stable alkyl, we must block the beta elimination pathway for decomposition. This can happen, for example, with alkyls that have no beta hydrogen, such as hexamethyl tungsten, or with 18-electron species with firmly bound ligands which will not dissociate to generate a vacant site, like this one in this example. We can also do it with alkyls for which the beta hydrogen is unable to approach the metal as a result of the geometry. For example, the vinyl and phenyl groups. Both have beta hydrogens, but they do not beta eliminate easily. One reason may be that the beta hydrogens are farther from the metal in sp2 carbon systems. In addition, the phenyl and vinyl groups have stronger metal carbon bonds than does the ethyl group. Finally, beta elimination is blocked in some D0 alkyl complexes, such as those of titanium-4. This last complex can serve as an example of what it is called agostic alkyls. In this species, all the criteria appear to be favorable, but beta elimination still does not occur. The reason that beta elimination does not occur in this case is that the D0 titanium has no electron density to back donate into the antibonding sigma orbital of the carbon-hydrogen bond. This back donation breaks the carbon-hydrogen bond in the beta elimination reaction, much as happens in oxidative addition. Agostic binding of carbon-hydrogen bonds also provides a way to stabilize coordinatively unsaturated species. Where beta elimination cannot occur, alpha elimination sometimes takes over. Alpha hydride elimination is a less common reaction with metal alkyls. A hydrogen atom on the alpha carbon is added to the metal to generate a carbene or alkylidine group and a hydride. It is also important to have an empty orbital fused to the alpha hydrogen in order to have the alpha hydride elimination. We have already studied different reactions which can be used to obtain alkyl complexes. Please have a look at some examples in your PowerPoint slides. Let's finish this unit with this slide about aryl complexes. Aryl ligands are relatively strong anionic, one-electron donor ligands, like alkyls. Since they cannot easily beta-hydride eliminate, metal-aryl complexes are usually relatively stable compared to alkyls with beta-hydrogens, but are usually quite air-sensitive. Aryls do have the potential for both pi donation and pi backbonding through the filled aryl pi orbitals and empty antibonding pi orbitals. This can provide additional stability to a metal complex, depending on whether the metal needs additional electrons from the ligand or wants to dump excess electron density onto the ligand. So we finish with this slide. Thank you very much for your attention.